Hi, I didn't see you there. I'm Mr. French, your AP Stats teacher. Let's do some AP Stats! Welcome back to Mathink. It is Mr. French here, your AP Stats teacher. I now have a mohawk, which is exciting. Thanks for the folks that are completing their Khan Academies, doing their suggested practice. So I look forward to finishing up these next few videos so we can start doing some review for the AP exam. We're going to get a lot more information for the AP exam come April, but until then, we'll just keep going with Chapter 6 for now. So we have two goals for this lesson today. Our two goals are to be able to determine whether the conditions for using a binomial random variable are met, and to be able to compute and interpret probabilities involving binomial distributions. So a big key word for today is binomial. Binomial. So let's just go ahead and define what a binomial random variable is. There are two types of random variables that are the most commonly looked at. The first one that we'll look at in this lesson is called the binomial random variable. In two more videos, there's going to be something called a geometric random variable. We need to be able to identify what's called a binomial setting. So I'm going to show you three scenarios that are all under what's called a binomial setting. I'd like you to think about what they all have in common. So here are the three. You toss a coin 5 times and count the number of heads. You spin a roulette wheel 8 times and record how many times the ball lands in a red slot. You take a random sample of 100 babies born in US hospitals today and count the number of females. Have you thought about what all those scenarios have in common? Let's take a look at a few. So we are going to go over the binomial settings. The first binomial setting we're going to establish as binary. Binary means the possible outcomes for each trial can be classified as success or failure. In other words, there are two outcomes possible. You either get the thing you're looking for or you do not. You toss a coin 5 times to count the number of the heads. So you count the number of heads, which means that there's only one other option, tails. Count the number of times that a roulette wheel lands on red. So it's either red or it's not red. So it doesn't just have to be two things. It could just be, did this one thing happen or did it not happen? Because on a roulette wheel, there are 3 colors, red, black, and green. But in scenario 2, you're just concerned on if it's red or if it's not red. So binary needs to be met. Another thing they all had in common was that each trial was independent. If you forgot what independent means, knowing the results of one trial must not tell us anything about the result of any other trial. When you flip a coin, just because it's heads, it doesn't change anything. When you spin a roulette wheel, it's not going to change anything if you knew that it landed on red. The next thing that they have, I'm going to say, is number. The number of trials, n, of the chance process must be fixed in advance. We flipped the coin 5 times. We spin the roulette wheel 8 times. We've got a selection of 100 random babies. So the number of trials needs to be established. The last thing we're going to look at is that they have the same probability of success each time. The coin will always be 50-50. The probability of red, 18 out of 38 each time. So the same probability of success needs to happen. You may recognize that we have an acronym that we can use. If you are trying to identify a binomial setting, check your bins. B-I-N-S. Binary. Are there only 2 outcomes possible? Independent. One must not affect the other. Number of successes. Trials fixed. Same probability of success. Here's our first example. Genetics say that children receive genes from each of their parents independently. Each child of a particular set of parents has a probability of 0.25 of having type O blood. Suppose these parents have 5 children. Let X be the number of children with type O blood. So let's check our bins. B, is it binary? In this case, yes, you either have type O blood or you don't. I, it does say that genetics say that you get these genes independently. Number, is there a fixed trial or a fixed number in this case? Yeah, they are going to have 5 children. So that is the number of children they're going to have. So that's a fixed number of trials. And then the same probability of success. Yep, because the probability is 25% on each trial. So in this case here, it is a binomial random variable setting. Let's take a look at the next example. You shuffle a deck of cards, turn over the first 10 cards one at a time. Let Y be the number of aces you observe. Is it binary? Yes, because it's either an ace or it's not an ace. So there's only 2 outcomes for this random variable. Independent? No. If the first card you turn over is an ace, then the next card is less likely to be an ace because you haven't replaced it in the deck of cards. And also, if the card was not an ace, then it'd be more likely that the next card was an ace. So this is not a binomial random variable. And if we checked the rest of them, there is a set number of trials in this example because you are picking exactly 10 cards before it happens. The probability of getting an ace on a shuffled deck is 4 out of 52, but the broken one here is the independence. Next example. You shuffle a deck of cards, turn over the top card, put the card back in the deck and shuffle again. Repeat this process until you get an ace. Let W equal the number of cards required. So W is the number of cards required it takes for you to eventually get an ace. Binary, yes, because it's either an ace or it's not. Independent, that's actually going to be okay this time because you're putting the ace back into the deck and then shuffling. The number of trials here is unknown because we're looking for the first time that we get an ace. We don't know if that's going to be on the first draw or the second or the third or the fourth or maybe doing it 100 times. But that's not set in this case. So the N is now broken. This is not a binomial random setting. Success, I mean, that's true because each time it's shuffled and the probability of getting an ace is 4 out of 52. So the first one was with the type O blood or not and having 5 children. And the last 2 weren't. The second one broke the independence because we didn't replace the card. The third one broke the number of trials because we were looking for our first ace and we didn't know when that was going to happen. So let's take a look at an example of how to calculate binomial probabilities once we've established that something is indeed a binomial random variable. We're going to go back to the blood type setting since we already established that that is binomial random variable. So here it is again. Each child of a particular set of parents has a probability of 25% of having type O blood. Genetics say that children receive genes from each of their parents independently. If these parents have 5 children, the count X of children with type O blood is a binomial random variable with N equals 5 trials and a probability of success of 25%. In this setting, a child with type O blood is considered a success, and a child with another type of blood is considered, quote, a failure. We'll define X as the number of children with type O blood out of 5. So we have our number of trials. This family is going to have 5 children, and we have a probability of success of 25%. So let's think about a few things. We're going to start with an easy example here. Let's calculate a few probabilities. Let's say I wanted to calculate the probability that X equaled 0. In other words, you have 5 children and none of them have type O blood. But really, this is equivalent to the probability of, so I'm going to say S for success and F for failure. So really, the probability that you have 0 children with type O blood would be 5 failures. And so how do we calculate these probabilities? Well, we know that the probability of the first kid, once again, we're trying to find the probability that we have no kids with type O blood. Now, the probability is 25% of having type O blood, which means that if they don't, then the first kid has a probability of 75%. The next kid is not going to have type O blood as well. we want this and this and this and this and this to happen. When and statements are happening, that means we can multiply probabilities. So you take the first outcome, times it, since it's an and statement, by the probability of the second outcome given that the first one occurred. But since these are independent, it doesn't matter that the first one occurred, which means that this next one will still be 75%. Once again, 75% is that they are not type O blood, which kind of makes sense that it's larger than 50% because there's a lot of other blood types besides just the one type. And that's going to continue on for the rest. And I can simplify this to 0.75 to the power of 5, which is about a 24% chance that if this couple has 5 children, that none of them would have type O blood. So I chose this one specifically because it was a fairly simple example. Ooh. Let's crank it up a notch here and let's think about what is the probability that this couple wouldn't have 0 children with type O blood, but let's say that they have 1 kid out of 5. So once again, they're still going to have 5 kids. What's the probability that they have 1 kid out of 5 with type O blood? Well, this is going to be equivalent to, well, let's think about a few things here. Remember, S is success, which means that they have type O blood, F is failure. So this is one scenario that can happen. And so the probability of this happening, this is saying that the first kid has type O blood, and then the last 4 don't. So we can take that same idea here. The probability that the first kid is going to have type O blood, we already know that is 25%. So I take 25. And now I'm going to multiply it by the next kid not having type O blood. So I take the probability that the second event occurs, given the first one occurs. But does that matter? No, because these are independent, so the probabilities do not change. Once again, if I want this and this and this and this and this, and statements you can multiply as long as you change the probabilities accordingly. In this case here, you don't need to change probabilities because we have independence. So if I were to write this, it would look something like this. This is one way that this could happen. The first kid could have type O blood, and the last 4 don't. Do you notice that there are more ways that this could occur? What if the second kid had it? What if the first one did it, the second one did, and the last 3 don't? Or what if the third kid had it, and the first 2 and the second 2 don't? Or what if the fourth kid had it, and the first 3 don't, and the last one doesn't? Or what if the first 4 don't, and then the last kid has type O blood? There is not one scenario that this could occur, but 5 scenarios that this could occur. So our success could be the first kid, the second kid, the third, the fourth, or the fifth. So this could happen, or this could happen, or this could happen, or this could happen, or this could happen. There are 5 different ways that this probability could occur. What do we do with or statements? We add them. We add up all of these together. But think about something here. Really, this, I could reduce and simplify the writing here to this expression. So 0.25 times 75% 4 times. Now the order of multiplication actually doesn't matter. Whatever number this is, it's going to be equivalent to this number as well. The order of multiplication does not matter. So it turns out that this probability is equivalent to this. And the same thing here. The order of multiplication doesn't matter. So each of these probabilities are actually all the same. So this multiplication is the same as this, is the same as this. So the order of multiplication does not change. So all 5 of these I could write as this. But there's 5 of them, which means I would have to add this to itself 5 times. I don't want to write out something added to itself 5 times. What's 3 added to itself 5 times? Well, that's 3 times 5. When you add up all of these, and since they're all the same number, when you do repeated addition, that is multiplication by definition. So this could be simplified to a multiplication of 5. In other words, in all 5 of these examples, you have 1 success, you have 4 failures, but there's 5 different ways that it could occur. So when you add up all of these, the probability that x equals 1, we say is 5 times 0.25. In other words, let's break down each of these pieces. This is the probability of success. This is failure. And this is the number of arrangements. And I could even put a little 1 here. So if you want 1 kid to have type O blood, this represents the 1 kid. This represents the 4 other kids, and this represents the number of ways that you could arrange that one kid out of the 5. And this probability is equal to, there's about a 40% chance that this couple should expect one kid to have typo blood out of the 5. Let's say now we have the same exact setting, but now we want the probability that x doesn't equal 1, but it's 2. I could think about just one simple case, and I'll have to think about the total number of arrangements. So I could do success, success, failure, failure, failure. From what we've seen, this probability, this particular outcome has a probability of 0.25 times 0.25, and then times the 3 failures here, the 3 students that don't have typo blood, and I could reduce this to 0.25 to the second, the third. But this is only one scenario. Think of how many ways could I arrange, so like the first 2 kids could have typo blood, but the first and the last kid could. The second and the third kid could, the second and the fourth kid could, the third and the fourth could. So how many different arrangements are there when you choose 2 things out of 5? Well, here's the total number of arrangements, and it turns out that there's 10. You would take this probability because each of these 10 outcomes here, each of these 10 outcomes has the same probability of happening. And so you just take this and you multiply it by the number of arrangements, which is 10. And so the probability that this family should expect 2 kids to have typo blood out of 5, about a 26% chance that this couple should expect 2 out of the 5 kids to have typo blood. But some of you are probably wondering, well, what if these numbers are like more complex? How am I going to get this number here? It'd be really nice if I could just think of like one scenario and then I could just come up with this number as opposed to writing them all out. Well, let's see how you can do that on your calculator. Here's another example. So I'm going to show you how to get this number on your calculator. So let's say that Mr. French gives you a 10-item multiple choice quiz. The catch is each student must simply guess the answer A through E for each question. Mr. French uses his computer random number generator to produce the answers to the key so that each possible answer has an equal chance to be chosen. Patty is one of the students in the class. Let's say X is the number of questions that Patty gets right. So let's write a few things down here. We do have a set number of trials here. It is a 10-question multiple choice test. The probability of success, well, it's a 1 out of 5, which is 20% chance. So I'm curious as to find the probability, cookies are done, that X equals 3. So in order to calculate this, I'm going to take like one particular scenario. Like you could get the first 3 right and then the last 7 wrong. Now I don't want to write that all out, so I'll just do this. So the first 3 right, you'd have 20% 3 times. So 20%, 20%, 20%. And then the last 7 of them would be failure. So if you're simply guessing, I'll just think of like the scenario where the first 3 are right, the last 7 are wrong. There's a lot of different ways. So I'm going to show you how to calculate this number here. In other words, how many ways can we arrange 3 things out of 10? So I'm going to show you how you can get this number on a calculator. This is what we do. So the number of ways we can arrange. So I'm going to show you how you can use your calculator to get this number here. The number, so how many ways can we arrange 3 things out of 10? Because we're going to arrange these 3 successes out of the 10. So the first thing we're going to do is you're going to type the number 10. Okay. Then you're going to go to Math, go over to Probability, and you're going to go to NCR. What NCR means is that this is your N, and this is your R. So it's going to tell you how many combinations are possible when you choose 3 things out of 10. So I'm going to choose option 3 for NCR, and then the number of things out of the 10. So it's the total amount, and then how many you're choosing out of that total. Different ways to arrange 3 things out of 10. There's 120 ways to get exactly 3 questions right and 7 questions wrong on a 10-question multiple choice test. And so this probability, the probability that X equals 3, And another notation that you should expect on the AP exam is something like this. This is the same exact idea. You're choosing 3 things out of 10. It's not a fraction. This is combination notation. So this tells you the number of successes. This tells you the number of failures. This tells you the number of ways that you can arrange those successes out of the total number. And this probability comes to about 20%. So this is just another way that you would see it. Now the number is 20. So what I would do is I would go 120 times 0.20 to the third times 0.80 to the seventh. This is the probability that Patty is going to get exactly 3 questions correct out of 10 on this test. Let's take a look at one more example. I think the examples are going to be helpful really here. So a local fast food restaurant is running a draw 3, get it free lunch promotion. After each customer orders, a touchscreen display shows the message, "Press here to win a free lunch." The computer program then simulates 1 card being drawn from a standard deck. If the chosen card is 3, the customer's order is free. Otherwise, the customer must pay the bill. Let's say that all 12 players on the school's basketball team come and order a lunch. So we're going to say that X is the number of players who win a free lunch. And we're going to say that N equals 12 for this team. And the probability of success in this case, it says if the chosen card is a 3. That is a 4 out of 52 chance. There's 4 3s in a 52 deck of card. So let's think about our bins. So B, well, the person's either going to get a free lunch or they won't. I, it is a computer simulation of choosing 1 card being drawn from the deck. So each time the computer's not going to take a card out. It'll reset the deck. So each trial is independent. And number of trials. Yes, N is 12. And it is the same chance of success each time. So there's always going to be 4 aces in the deck at all times. So we have 12 people going up to buy a lunch. I'm curious as to, on this 12-person team, what is the probability that exactly 2 of them win a free lunch? So I'm going to think of the simplest case first. The first 2 win and the last 10 don't. So I'm going to write that like this. The first 2 are going to win. So probability of success is 4 out of 52. So the first 2 have that probability of success. And then the last 10 do not. So that's 48 out of 52. So the number of ways that I could arrange 2 things out of 12. Remember, there's 12 people on the team. So how many ways could I arrange 2 successes out of a 12-person team? And so this is the notation you should be able to read. And when you type it into your calculator, I'm going to start with this first. So I'll start with 12. I'll go over to math, go over to PRB, option 3, which is combinations, and then 2. So this is 12, choose 2. And the number of ways that you could choose 2 things out of 12 times the probability of success squared, because I'm looking at the 2 successes, times the probability of failure. And if there's 2 successes, there's 2 free lunches, it's going to be 10 people that have to pay. And so we get the probability that X equals 2, the probability that we have 2 people on the team that get a free lunch is about 18%. There's about a 17.5% probability that exactly 2 players will win a free lunch. We still have a lot of examples. I'm going to assign some suggested practice. Here is your suggested practice for 6.3, day 5. You should be able to recognize a binomial setting, and you should be able to calculate binomial probabilities. This was a lot. Hope you're having a good day. Keep practicing. Please respond or comment on the Google Classroom with any questions that you have so we can share those questions. Thanks for your time. This has been Mathink.